Transistor biasing. Biasing is applying proper supply condition, that is power supply conditions, to a device so that we can operate that particular device in desired manner, right? Maybe we can turn it on, we can turn it off, right? And so that we can achieve the operation that is we are required in particular circuit, right, or particular application, right? So similarly, we have three regions or three modes of operation of transistor, right? Active region, cutoff region, saturation region, right? So to operate those transistor within these three regions, we have to set those particular voltage and current conditions, right, along these transistor terminals, right? So according to the required mode, we should apply that particular supply voltages, right? Let us see uh, how biasing is going to affect or why biasing is needed for transistor. Right? Suppose this is the characteristics, right? This is the plot or the characteristics of particular BJT amplifier. Right? So it is going to have three regions, right? So from this line, right? Yeah, this vertical lines, right? This vertical lines represents what? Cut off region means below this transistor is in off condition, right? And this horizontal purple line, right? This horizontal purple line below this straight line, right? This is saturation region, right? Where the transistor is in saturation and maximum current is going to flow, right? And we will get the maximum current at output, right? And when it is going to cut off region, there will be no current at the no voltage at the output at collector, right? While this remain region of yellow, yeah, yellow lines or these red lines, right? What it indicates? It indicates the activity, right? So yeah. So what is we can what we can conclude is that it is nothing but the set of points of VCE and IC, right? Collector current and the collector voltage that has been applied to this transistor, right? So these are the values of the value of IC and VC, right? So according to that, we get these different regions, right? So a transistor to work as an amplifier, we have to operate in active region, right? So before after this line, right, after this point, right, it is going toward this saturation region, and after this point, right, after this point, it is going toward this cutoff region, right? So within this cutoff region and this saturation region, we can use it as transistor. But if we have to use it as amplifier, we have to operate all this value of IC and VC within these two points, right? Within this segment, right? Yeah, within this region or reactive region. So we have to maintain the voltage VCE across but that collector emitter, right? Yeah, that is should be equals to all this point that is to be present within this region, right? So then and only then uh, we are able to operate this transistoring amplifier. Otherwise, it will be in this saturation mode or off mode, right? So what is all those collection of points, right? All those collection of points, this blue line, right, indicates this set of points where we have to operate our transistor so that um, this particular operation of that transistor can be controlled within either in amplifier mode, cutoff mode, or saturation, right? So if we have to use this transistor in amplifier mode, we have to operate the transistor or we have to maintain the voltage across the transistor current across within the transistor that is going to be equal to the all those value of the set of point of this blue line. Okay, so we call this line as DC load line. Okay, we call this line as DC load line. So we are going to operate the values of the transistor in direct current, right? DC values, right? We are providing DC supply to this collector, right? Collector terminal we see, right? So for all those set of points, these are the points when we get for what DC values or DC supply, right? Okay, and load line means we have to operate a certain load or operate a certain device along this collector of this transition, and for the purpose we have to maintain what that particular values, and otherwise that particular transistor will not able to drive the further load of the device or that will be created at the output. So that's why we call it as DC load line. All the set of point which are used for operating the transistor, right, in this fully operational mode, right, in amplifier mode, or between saturation or cutoff. So full operation. Right? So if we formulate the relation between the IC and the voltage applied VCC, right? So it will be get like IC equals to minus 1 upon RC into VCE plus VCC by RC. Okay. So this is a very basic equation that we are putting apart. Okay. So suppose yeah, if we put IC equals to 0, if we put IC equals to 0, then the value VCE becomes equals to VCC, right? And similarly, if we put VC equals to 0, right? So we will get a maximum value of IC, right? Okay. So likewise, we have the maximum and minimum value of IC and VC, along which we have to set the value of this uh, operating conditions of the transistor. So if we have to operate this particular transition amplifier, so we have to operate these values, right? We have to operate or we have to maintain the values from this point to this point. So like this, okay, A to B, right? So whenever input IV current is going to vary, whenever an input current IV current is going to vary, right? Like this, suppose this is considered, right? So similarly, the output collector, that is, so yeah, I see, that is going to vary, right? So that is going to vary. So it is going to vary in all the possible values, right? So yeah, like this, okay. And suppose before this A point we have got yeah, saturation region, below this B point, right, we have cut off region. So definitely we have to operate the current or voltage we see within this point of the segment A to B, right, within which the transistor will be in amplifier mode. Otherwise it will be in cutoff mode, and above this A point it will be in saturation. So if the current that is going to be present between this range of values. So if IV, whatever the IV current has been applied, and we, that whatever the IV current is going to vary, similarly IC is going to vary. So we need that. So we need that IC value. We need that IC value should be present between what point A to B. Similarly, VC should be present between A to B. All right. So the this value is going to vary between this segment A into A and B, right? So we call that point as a Q set point. We call that point as Q set point. Okay, so it is nothing but what IC and VC. Q set point is nothing but value of IC comma VC, right? It is nothing but plot of IC and VC, right? So Q is Q set point divided by Q, which is nothing but point divided by value of IC and VC. So within the segment A to B, what we have to maintain value of IC and VC, and we call this point as Q set point. So suppose this quiescent point, suppose this quiescent point is above this point A, so it will operate this transistor reach in saturation region, right? If this point Q is present below this peak, so the transistor will be working in cutoff region, right? So in order to maintain the transistor in amplifier mode, so we have to maintain this value of Q by CPC within this A to B segment, right, in amplifier region, so that we will get this value of IC. Otherwise, with respect to changing this input current, suppose with respect to changing input current ib, if the value of ib exceeds, right, this segment a, and if it again exceeds the segment point b, right, so what will happen, see, so what will happen if input current is out of the range, right, like this, so we will in the saturation region, no, at this point, right, the current will be, in this saturation region, so the information will be cut off, right, this portion will be cut off. Similarly in cut off region, right, it's like was this, if the input signal is out of range, right, so the output current I see here at this point, it will get cut off, right, so there will be cut off of the signal for whatever the input applied. We will not get the perfect perfect output, right, if we don't yeah don't operate this input current within this range, right? Whatever the required range of this quiescent point, so that we will get the quiescent point within this DC load line segment, right? If we don't operate the input base current in such a manner that the Q point is out of this DC load line segment, right? So we will get the output signal IC or VC cut off, right? It will get cut off. So our signal shape has changed. So information has changed. So which is not required. So which is not desired, right? In any operation where our signal is going to, change its shape or is going to lose this information, right? Is going to deform, right? So that's why we have to maintain this input signal within a particular range. We have to maintain this input signal within a particular range so that we should get fully output, full output, right? Full output, right? So that we should not um, uh, hamper the output, we should get the complete output. So that's why according to this q set point, we have to also maintain this input base current values. Okay, so that's why we have to maintain the base to emitter voltage current, and at the same time collector to emitter voltage and IC current, right? So that's why biasing is very important. Otherwise we will get this signal cut off, or the information will get lost, right? If this is the input signal, so the signal will be look like this. If it is not in proper conditions, it will get saturated. Okay, so output will get saturated. Okay, maximum output, we will get the maximum output here, we will make the maximum output here. So you can say that all those values, right, for all those whatever the values where maximum voltage is you know um, getting at the output, so that value is going to cut off. So when we get the maximum value, so at saturation, right, saturation region, right? So that means the maximum value is this, after which we will not get any maximum value. Suppose the transistor is having gain of suppose 5, gain of 5, and input signal is having the voltage of 1 volt. Input signal have is voltage of 1 volt, and the amplifier is having the gain of 5. So and the and the supply voltage is of 10 volt, right, and the supply voltage of 10 volt. So 1 into 5 will equals to 5 volt, right? So we have the 10 volt supply, so we can produce 5 volt output, right? We can produce 5, so we will get maximum output, right? But suppose input voltage is 3 volt. Suppose input voltage is 3 volt, gain is 5, and the applied voltage is 10. So 5 into 3 is equal to 15 volt. 5 is equal to 5 into 3 is equal to 15 volt, right? So we have only 10 volt. So how we can get 15 volt at the output? So we will get a maximum 10 volt only. We will not get 11, 12, or 15. We will get maximum 10 volt, right? Positive 10, negative 10, whatever. Yeah, so similarly current will be limited, so we will get the maximum, right? So this is what saturation is. This is means the transistor of the region saturation, it is providing us maximum value. If the gain is not if gain is maximum and if input current range is maximum, right, so it will produce a maximum out. So transistor will be in saturation and we will get a saturated output or cut off output, so like this. So for that purpose we have to maintain the gain and these input the current, right, input current or whatever the base value and the collector current value and the collector voltage value, we have to maintain it properly so that we should get the proper amplified signal, right? So this is what the biasing is. So that's why biasing is needed. Okay. Yeah. So we have the different type of biases: fixed bias, collector bias, self bias, right? That we will see in next lecture.